This is B Naresh, working assistant professor in AC department. And today's topic is transistor current components and relation among current gains. So in this session, we are going to observe what are the current components and what is the relationship between those current components. So for this case, before going to this session, we have this. So we have the two types of the transistors. One is either NPN transistor, another one is a PNP transistor. And based on that, we have the three modes of configurations. One is common base configuration, common emitter configuration, and common collector configuration. And if you know this, the common base configuration, let us take, I consider a NPN transistor, and we know this is base, collector, and emitter. So means, and input is passing through this base terminal, and it is biased with plus VCC. Output is taken from the collector, hence it allows the collector current, and here the base current is the flows, and occur this a emitter current, IE. So then, similar to that, if we take a common emitter, sorry, this is not the common base. So in the common base, the base is a common. Let's take this is base, emitter, and the collector. So base is a common for input and output. So the input is passing through emitter terminal, and this is NPN transistor, emitter, base, and the collector, N-type, P-type, and N-type material. And output is taken from the collector. So then the base current is flows here, and the collector current is, this is collector current, and here emitter current. Means output is, in this the output is collector current and the input is emitter current. Similar to if you draw the common emitter, this is common base. If you want to do the common emitter, and emitter should be common for input side and output side. Let's take this as VCC. And input is passing through the base terminal, and output is taken from the collector terminal, and then it is emitter current to the flows. This is base and collector current. And at this point, the collector current is acts as the output, and the base current is acts as the input. And this is for common emitter configuration. Similarly, if you want to take the common collector, so for this common collector, output is taken from the emitter, and the collector is a common with respect to the input and output. Base is acts as the input, collector, base, and emitter. So in this case, in a common collector configuration, output is acts as the collector current, so emitter current. Input is acts as the base current. So based on these three configurations, we need to find out a current gain. So in generally, the current gain or a DC current gain is defined as it is the ratio of output current to the input current. So hence, for this case, then the DC current gain is also called as here the current amplification factor. Hence, in a transistor amplifier with an AC input signal, the ratio of change in output current to the change in input current is known as the current amplification factor. Then, based on the configuration, so we have the three types of the configurations: common base, common emitter, and common collector. So in the common base configuration, that amplification factor is defined as or DC current gain is also defined as alpha. Means it is defined as the ratio of output current to the input current. So let me observe in a common base. So in a common base configuration, the input current is represented as emitter current and output current is defined as collector current. So hence, it is a ratio of output current to the input current. So means the rate of change of collector current with respect to the rate of change of emitter current. Here it is defined as a DC current gain or also called as current amplification factor in a common base configuration. Similar to that, if you define the DC current gain or amplification factor in a common emitter configuration, so if you observe the common emitter configuration, the output terminal is acts as a collector terminal. Hence, across the output terminal, the current is flows collector current, and input terminal is acts as a base. So hence, we are going to observe the base current, that is IB. And here it is defined as beta. So hence, the beta is defined as it is a ratio of output current to the input current. So here the output current is a collector current, hence collector current, and input current is base current. So hence, it defines or states that the rate of change of collector current with respect to the rate of change of base currents. Hence, the beta is defined as delta IC by delta or dou IC by dou IB. Similar to that, we have another configuration, that is common collector configuration. So in this, the common collector configuration, the current amplification factor or DC current gain is defined with the gamma. So if you observe this CC configuration, the input parameter is a base, so hence the current flows across the input terminal is base current. In this common collector, the output is represented as emitter, so hence the output current across the terminal is IA. For this case, now we need to define the gamma, means DC current gain, means it's the ratio of again output current to the input current. Hence, so here we taken as output current is a emitter current and the input current we consider as a base current. Hence, it is defined as the rate of change of emitter current with respect to the rate of change of base current, that is the DC current gain or amplification factor for a common collector configuration. Then we need to find out some. So till now we observe the three parameters, alpha, beta and gamma. Then we need to find out the relationship between alpha and beta. So how we can represent this alpha in terms of beta or beta in terms of alpha. So for this case, let us consider, we know that the emitter current from the transistor construction, the emitter current is represented as the summation of base current and collector current. So hence, here I represented as I is equal to IB plus IC. And from this, again from the common base configuration, if you want to write this mathematical relation in a common base configuration, the input terminal is acts as the emitter. Hence, the emitter current we taken as the input current. Again, in a common base, the output terminal is we taken as collector. So the current across the collector terminal is IC. From that, we know that the generalized expression for this common base is represented as alpha times of IE plus ICBO, where the ICBO is a reverse saturation current, or when that is a collector base junction is open circuited. Hence, the reverse saturation current is a very, very small. Hence, we are going to neglige it. Hence, IC is approximately equal to alpha times of high. So from that, here I represented as IC is equal to alpha times of I. Now you can substitute this IC value in this relation. So hence now I'm going to consider the same equation. I is equal to IB plus IC. Now I'm going to substitute this in this relation. So what happens? This IE becomes IB plus alpha times of I. So hence here I substituted this IC value that is equal to alpha times of I. Now we can make the common terms. So here we have the two common terms. What is that? IE and alpha times of IE. So means IE minus alpha times of IE, that is equal to IB. So here if I is the common, then it becomes 1 minus alpha, that is equal to IB. So hence here I represented as IE is a common, 1 minus alpha, that is equal to IB. So again from this I'm going to observe this equation. In both sides I'm going to divide with the above equation divided by IC with means divided with IC numerator and the denominator. So hence to observe means why I'm going to divide with IC, to observe the ratio this alpha in terms of beta. So hence this I'm going to divide with IC. So IE 1 minus alpha is divided with IC, that is equal to again IB by IC. So from this, if you know this one, so in this case, if you observe this IB by IC and just now we observed some three parameters, alpha and beta and gamma. So alpha means, what is alpha? We observe is the ratio of output current to the input current. So in a common base, so IC by IE. Beta means in a common emitter, that is common emitter means IC by IB. Gamma means it is a common collector, so hence IE by IB. If you observe these two relations, alpha and beta, alpha is defined as IC by IE, beta is defined as IC by IB. So hence, so this factor I can write this is 1 by alpha. So this is actually alpha is IC by IE. Now I'm going to write this is 1 by alpha. And similarly beta is IC by IB, but we have IB by IC. Hence, I'm going to write IB by IC. So hence means 1 by beta I'm going to write here. So then, so hence here I'm representing with so then this is 1 minus alpha means this factor I replace it with 1 by alpha, and this is equal to means this parameter I'm going to write 1 by beta. Now, so we can write here, so this is 1 minus alpha by alpha, that is equal to 1 by beta. So now I required, so I'm going to relate this beta in terms of alpha. So hence I'm going to derive this relation from this one. Beta is equal to, you can write alpha by 1 minus alpha here. So that is the reason. Beta is equal to alpha by, so here by using this a transistor current expression, and we convert this alpha value means the beta we can represent it in terms of alpha. Similarly, now we can also write alpha in terms of beta. So this is the relation beta in terms of alpha. Now we are going to write the relation alpha in terms of beta. For this case, let us consider again the same current expression. So I is equal to the summation of base current and collector current. For this case, we know that again, so in the previous case, what we observed, we assume this is IC is equal to alpha times of IE. So this is I taken for the common base configuration. If I consider from the common emitter configuration, we know that IC is equal to beta times of IB. So why with that I'm going to write alpha in terms of beta. So hence here I assume this the IC is equal to beta times of IP. So hence you can substitute this one in this relation. So means IE is equal to IB plus IC. Here I am going to substitute IE is equal to IB plus beta times of IB. Now here we have these two common terminals, hence IE is equal to, if IB is a common, then it is represented as 1 plus beta. So hence, now this one I am going to derive with again to convert in terms of this beta, so this alpha in terms of beta. So again I'm going to this divided with the IC in both the cases. So hence I'm going to divide with the IC. So IE by IC, that is IB times 1 plus beta by IC. So in this relation, now again if you recall this, the amplification factor DC current gain from the transistor configurations, alpha is defined as, so means this alpha is derived from the common base configuration. So alpha is means it is the ratio of output current to the input current, that is IC by IE, and beta means in a common emitter. What is a common emitter? Means output is collector current and input is base. Now you can observe again this one, this IE by IC means, so that is reciprocal of alpha value, and similar to this IP by IC means again this is the reciprocal of the beta. So hence we know this 1 by alpha, that is, so here this is alpha. You can, if you want to write 1 by alpha, that is IE by IC. Suppose if you want to write 1 by beta, that is IB by IC. Hence I'm going to replace with this parameters here. So mean this one we assume this 1 by alpha, hence 1 plus beta by, this is nothing but a 1 by beta. Now we require this alpha in terms of beta. So hence I'm going to write alpha means that is beta by 1 plus beta. Just to revert this one. Hence the alpha is represented as beta by 1 plus beta. So up to this point, we observed some relation, alpha and the beta relation. Alpha in terms of beta, that is beta by 1 plus beta, and previously we observed beta in terms of alpha. Beta is equal to alpha by 1 minus alpha. These are the two relations between alpha and beta. Alpha in terms of beta as well as beta in terms of alpha. Now similar to that, we need to find out the relationship between three contingent parameters, alpha, beta and gamma. Now we need to identify the relationship between how we are going to write alpha in terms of gamma or beta, or beta how to write in terms of alpha and gamma, like that. So for this case, if you know this relation, so from the transistor configurations, so in this case we identified that in a common collector configuration, the DC current gain or amplification factor is defined with a gamma. So it is a ratio of output current that there in a common collector configuration, the output terminal means output is measured across the emitter terminal and input is passing through base terminal. Hence it is defined as IE by IB. So hence I consider first the gamma value. So till in the previous case we observed the relation between alpha and the beta. Now I'm going to write this gamma in terms of alpha and as well as beta. So hence, so here first I assume this the DC current gain of the common collector transistor, that is gamma is equal to the ratio of emitter current to the base current. Now we know this from the transistor construction, the emitter current is represented as the summation of base current as well as the collector current. Now I'm going to substitute this in a IE value. So hence gamma is equal to IB plus IC by IB. Hence, or otherwise we can substitute this IB value here. So suppose from this if I assume this one, if you are assuming this IB is equal to, from this relation IB is equal to IE minus IC. So now, so gamma is equal to IE by IC, so IE by IB So this is IE by. So IB means we assume the difference between emitter current and collector currents. Hence, this is IE minus IC. So hence, here it is represented as gamma is equal to IE by IE minus IC. Now, I'm going to divide this factor, denominator and numerator is divided with IE value to observe some relation. So hence, gamma is equal to IE by IE by, again this is IE by IE minus IC by IE, hence denominator and numerator is divided with IE here. So now from this relation IE by IE by means 1, again this is get cancelled 1 minus IC by IE. And based on this, again if you recall the current gains of the transistors, we have alpha, beta and gamma. So alpha is derived from the common base configuration. Here it is defined as it is the ratio of output current to the input current, that is IC by IE. Beta is IC by IB. Gamma is IE by IB. So if you observe this one, means this IC by IE is nothing but your alpha, means this parameter is nothing but here it is represented as. This ratio we can replace with the alpha value. So hence the gamma is equal to 1 by 1 minus alpha. So this is 1 by 1 minus alpha, means the gamma is represented in terms of alpha. So that is gamma is equal to 1 by 1 minus alpha. Now if you want to write in terms of beta, if you want to express this gamma, so this is the expression for gamma in terms of alpha. If you want to express this gamma in terms of beta, then again I taken this one, the same relation, the current gain of common collector configuration. Based on that, the output current is represented as emitter current and input current is base current. Then again we know that I is equal to IB plus IC. Here I'm going to substitute here. So this IE value, so previously I substitute the IB value. Now I'm going to substitute this IE value. So what is IE value here? So means from this gamma is equal to IE value is IB plus IC by the IB is IB. So hence it is defined as gamma is IB plus IC by IB. So from this, now I'm going to divide with IB. Denominator and the numerator is divided with IB value. So hence gamma is equal to, means this is IB by IB plus IC by IB divided by IB by IB. So means what happens, this is 1 plus IC by IB divided by 1. So then again if you recall the DC, so if you recall this current gains of the common base, common emitter and the common CB means alpha is defined as IC by IE. In a common emitter that is defined as IC by IB, and the common collector that is IE by IB. If you observe in this relation, we have this IC by IB term. So means this IC by IB term is related to beta parameter. Hence, this gamma is equal to 1 plus beta by 1. That is nothing but your 1 plus beta. So up to this point, we observed in the two cases, the gamma is represented in terms of alpha as well as this gamma is represented in terms of beta. So from these two observations, gamma is written as either 1 by 1 minus alpha, or we can also write 1 plus beta. So this is the relation between the three parameters, that is alpha, beta and gamma. So means from all these three observations, what we observed, alpha is equal to beta by 1 plus beta, beta is equal to alpha by 1 minus alpha, gamma is equal to 1 by 1 minus alpha, or we can also write 1 plus beta. So these are the three important relations between all the three DC current gains from the configurations like common base, common emitter and common collector configurations. Now we'll see some of the problems based on these current components and the current gains. Let us consider a transistor has IB is 100 microamperes and IC the 2 milliamperes. So we need to solve the beta and alpha and emitter current, and IB the changes by plus 25 milliamperes and IC the changes by 0.6 milliamperes, and find the new value of beta. So for this case, the given specifications are IB is 100 microamperes and IC is 2 milliamperes. We need to calculate alpha, beta and gamma. Sorry, we need to calculate only beta and alpha. So then we need to calculate emitter current. So just now we discussed that the DC current gains or amplification factors for all the three configurations. So in a CV configuration, common emitter configuration and a common collector configuration. In a common base, the referential is the alpha is defined as output current to the input current, that is IC by IE. And in a common emitter, that is beta is defined as it is the ratio of output current to the input current, that is IC by IB. So hence, based on the given specifications, first I am going to calculate this beta of the transistor. So what is the beta? It is the ratio of collector current to the base current. So hence IC value is 2 milliamperes, 2 into 10 to the power of minus 3 divided by IB value is 100 microamperes. You can solve this ratio, it gives the beta value. Now we can alpha. How to calculate the alpha? So we discussed some relations between the three parameters. Alpha in terms of beta, that is alpha is equal to beta by 1 plus beta. Beta is alpha by 1 minus alpha. Gamma is either 1 by 1 minus alpha or 1 plus beta. Now we need to calculate this alpha. So we have only the beta. So hence I am going to write this alpha in terms of beta, that is beta by 1 plus beta. So you can substitute this beta value here to get the alpha value. Then after that, we need to calculate the emitter current. How much emitter current is the flows in this circuit. So we know that generally IE is equal to the summation of base current and the collector. So base current is 100 microamperes and the collector current is 2 milliamperes. So now you can solve this one, then it gives that IE. Now again, another problem. A common base connection, the emitter current is 6.28 milliamperes and the collector current is 6.20 milliamperes. Estimate alpha, beta and gamma. So means we discussed that some relations between alpha, beta and gamma, but they are given that in that only the common base configuration means. So in a common base configuration, we know that alpha is equal to the ratio of collector current to the emitter current. That gives the common base DC current again, that is alpha. So hence IC value they given that 6.2 milliamperes, 6.2 into 10 to the power minus 3 by IE value is 6.28 into 10 to the power minus 3. Then we need to calculate beta and the gamma. So just we discussed the beta and gamma, relation between alpha and the beta gamma. So what is the relation? Alpha is equal to beta by 1 plus beta. If you want to calculate beta in terms of alpha, that is alpha by 1 minus alpha. If you want to calculate the gamma in terms of alpha and the beta, that is 1 by 1 minus alpha or 1 plus beta. So hence, to calculate this beta, we have this alpha value. Hence, you should represent this beta in terms of alpha value, means alpha by 1 minus alpha. Just substitute your alpha value to get the beta. Then to observe this gamma, so what is the gamma? Either you can use 1 by 1 minus alpha or you can use 1 plus beta. Means either you can substitute this alpha value or you can substitute this beta value to get the gamma. Then the another question is the reverse leakage current of the transistor when connected in a CV configuration, that is 0.2 microamperes and it is 18 microamperes when the same transistor connected in CE configuration. Solve alpha and beta of the transistor. So we have the two configurations. So in the first case, CB configuration. In the second case, we have the CE configuration. So we know that in a CB configuration, The collector current is represented as IC is alpha times of IE plus ICBO. This is a generalized expression. If you want to convert this is in terms of CE, how to write in the CE, that should be represented in the CE configuration, that is IC is equal to beta times of IB plus 1 plus beta times of ICBO. Or we can also write IC is equal to beta times of IB plus ICEO. To understand, if you compare these two relations, from these two relations we know that ICEO is equal to 1 plus beta times of ICBO, where ICEO means the reverse saturation current or leakage current when the transistor is connected in a common emitter. ICBO means when the transistor is connected in a common base, that is a reverse leakage. That means from the given specifications, they given as 18 microamperes when the transistor is connected in C, means ICEO means 18 microamperes, means 18 into 10 to the power minus 6, that is equal to 1 plus beta times of ICBO, means the reverse leakage current when the transistor is connected in common base. So what is the common base? That is 0.2 microamperes. Now from this we can write 1 plus beta is equal to 18 into 10 to the power of minus 6 by 0.2 into 10 to the power of minus 6. That gives 1 plus beta is equal to 90. So beta means that is 89. So we observe this beta value. Now we need to calculate alpha. So we know some relation beta in terms, alpha in terms of beta. What is alpha in terms of beta? That is alpha is equal to beta by 1 plus beta. You can substitute the beta value to get the alpha condition. Then a transistor operating in a CB configuration has IC is a 2.98 milliamperes, IE is a 3 milliamperes, and IC naught is 0.01 milli. Then solve the which current will flow in the collector circuit of the transistor when connected in a CE and the base current is 30 microamperes. So for this case, so just when observe means from the CB configuration, IC is equal to alpha times of IE, then plus ICBO. So from this, first identify the alpha. So alpha means IC minus ICBO by IE. So IC means 2.98 into 10 to the power of minus 3 minus ICBO or IC naught is both are same, means that is 0.01 into 10 to the power minus 3 by the emitter current is 3 milliamperes, 3 into 10 to the power minus 3. Then you can get the alpha. Now, like that, so then we need to calculate the base current. So base in terms of, DC current again beta. Beta is in terms of alpha, means alpha by 1 minus alpha. Then after that, now we need to correct collector current, means in terms of CE, we know that IC is equal to beta times of IB plus 1 plus beta times of IC naught. So substitute the beta value here. So this is the alpha value. You can substitute the alpha value to get the beta. And here you can substitute the beta value and IB value. So here the IB value they given that 30 microamperes. So hence substitute beta and IB value and IC naught value that to get this IC collector current. Now a certain transistor has alpha of 0.98 and the leakage current is IC naught is 25 microamperes, and find the collector and base currents when IE is 2 milliamperes, means they given that alpha is 0.98, reverse saturation current is 25 microamperes. Now the emitter current is 2 milliamperes. Now we need to find out the collector current and base currents. So generally from the given specifications, we know that IC is equal to alpha times of IE plus IC naught. So means alpha value is 0.98, IE value is 2 milliamperes plus IC naught is 25 into 10 power minus 6. Then it gives that IC. Then after that you can calculate the base current. So we know that from the transistor current, IE is equal to summation of base current and the collector. So hence here the base current is the difference between emitter current and collector current. So you substitute emitter collector and collector current here. the substitute the IE value. So IE value is 2 milliamperes minus IC value, you can substitute here, then observe the IB. Then a transistor has IE is 10 milliamperes, alpha is 0.98, and find the values of IC and IB. So here the given specifications are IE is 10 milliamperes, alpha is 0.98. Now we need to calculate IC and IB. And from this we know that alpha is defined as the ratio of collector current to the emitter current IC by IE. So from this they given that alpha is 0.98. Now IC is unknown parameter. IE is 10 milliamperes, 10 into 10 power minus 3. So means from this IC is equal to 0.98 into 10 to the power of minus 3. So means IC is equal to 9.8 milliamperes. Then we need to calculate the base current. So to calculate the base current, so IE is equal to summation of base current and the collector current. So from this, the base current is the difference between emitter current and the collector current. So IE is 10 milliamperes and IC is 9.8 milliamperes. Hence the base current is 0.2 milliamperes. Oh, this is already we discussed. Now here, if a transistor has a value of alpha is 0.97 and find the value of beta. If a beta is a 200, find the value. So here, they given that alpha is a 0.97. Now we need to calculate the beta. So we observed, in this session we observed the relation between alpha and the beta. So beta in terms of alpha, beta is alpha by 1 minus alpha, means that is 0.97 divided by 1 minus 0.97. It gives the beta. In a second case, they given that beta is a 200, then we need to calculate alpha, means now we need to write this alpha in terms of beta, means alpha is equal to beta by 1 plus beta, means 200 divided by 201, that gives the alpha case. Now a transistor has beta is 100 and the collector current is 40 milliamperes. Now find the value of I. So means, so beta means we know that it is the ratio of collector current to the base current. So means in a common emitter configuration, the output is a collector current and the base is input current. So for this case, so we know that beta is equal to 100 here. IC they given that 40 milliamperes. So now we need to calculate IB first. So from this, the IB is equal to 40 into 10 to the power of minus 3 by 100. Then we will get the IB value. Then after that, you can find out this IE is equal to IB plus IC. Substitute this IB value and IC value to get the emitter current. Now, in a common base transistor circuit, the emitter current is 10 milliamperes and the collector current is 9.8 milliamperes. Now, find the value of base current. So, simply the base current is the difference between emitter current and the collector current. So, IE is 10 milliamperes and IC is 9.8 milliamperes, that is equal to 0.2 milliamperes. We'll see a transistor has IG is equal to 10 milliamperes, alpha is 0.98. Now determine the values of IC and IB. So here the given specifications are IE is 10 milliamperes, alpha is 0.98. Now we need to calculate IC and IB. So based on the given configurations, we know that one relation IC is equal to alpha times of IE. So means alpha value is 0.98 and IE is 10 milliamperes, 10 into 10 to the power minus 3, then it becomes 9.8 milliamperes. And similarly, we know that IB is equal to the difference between emitter current and collector current. Just substitute this IE values, means 10 milliamperes minus IC value is 9.8 milliamperes, that is equal to 0.2 milliamperes. Now, a transistor has beta is a 150. Find the collector and the base currents. If means beta is 150, then IE is 10 milliamperes. Now find out the IC and IB. So for this case, I can write this beta means we know that beta is equal to the ratio of collector current to the base current. So now here again there is no a. So here the beta is a known parameter, IC and IB is unknown parameter. So hence first again one more relation we have, IC is equal to alpha times of IE. But here IE is a known parameter. So hence first we need to determine this alpha parameter. So how to calculate this alpha? Alpha in terms of beta means beta by 1 plus beta means this is 150 by 1 plus 150. Then first you determine this alpha. Then you can substitute into this relation, IC is equal to alpha times of IE. Substitute this alpha value here and IE value is a 10 milliamperes. Then get the IC value. Then after that you can calculate this base current, that is the difference between emitter current and the collector current. So substitute emitter current and your collector current to get this base current. Now, the DC current gain of the transistor in a CE mode is 100. Determine its DC current gain in a CV mode. So means in a common emitter, the DC current gain is beta is 100. Now we need to calculate DC current gain in a CV means alpha. We need to calculate means alpha is equal to beta by 1 plus beta. Just substitute the beta value here. Then you can get the alpha value. So up to this point in this session, we observed that current components and current gain parameters and the relationship between some three parameters like alpha, beta, and gamma. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.